Really? Okay, so that's Vesper. It's valence shell. Switch these. Electron pair repulsion. So VSEP-R, not this. All right. So for this, we're going to discover what geometries our molecules are. For example, we have CH4. And the first step is to draw the Lewis structure, which when you draw that, it looks like this. And then there are two geometries to look at. One is the molecular geometry, and the other one is the electron geometry. Electron geometry shows you everything, including any lone pairs. Kind of what shape would it be then if you include the lone pairs? Molecular geometry shows you just the atoms, like what shape are the atoms, and it doesn't really do anything with the lone pairs. So, and I'll go into more detail. So I'm just kind of summarizing it, and then we'll go into detail here in a second. So looking at this, I can see there are 4 atoms attached to it, which means it's going to be tetrahedral. And so the shape would look something like this. With a carbon in the middle, like that. And then the angles are going to be 109.5. So basically what we're doing today is we're learning how to do that with different molecules. So go ahead and in a separate tab, pull up your textbook. I'll give you a second to do that. And go to section 5.2.
I have a question, Professor Kelly.
Sure, go for it.
What are the different types? I've forgotten them. There's tetrahedral. Is it trigonal plane?
Oh, yeah, there's trigonal planar, tetrahedral, trigonal bipyramidal, I think there's octahedral, T-shaped. There's a bunch of them. If you go to section 5.2 and scroll down to the bottom, there's a table there, and the table is going to show you all of the different types there are. So there's trigonal planar, bent, tetrahedral, trigonal pyramidal, another bent structure, trigonal bipyramidal, seesaw, T-shaped, linear, octahedral, square pyramidal, square planar. Yeah.
I'm only seeing linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, and octahedral. Is there only the 5?
Yeah. Look over to the the 4th column there, where it says molecular geometry.
Which page would that be? I have the book, not the online.
The actual book. Okay. Let me look and see if I can figure that out.
5.2, you said?
Yeah, okay, now I can see the page numbers. It's page 206.
206. All right, my bad. Yep. Thank you very much.
You're welcome. All right. So give me 1 second. I'm just looking at section 5.1. I looked at it earlier, and I didn't really see much that I wanted you to really... I mean, there's not a whole lot in there. One thing that it talks about is the shapes of the molecules. And hang on 1 second, Spencer, and I'll let you ask your question. So the different shapes of the molecules will do different things. So they have a theory that molecules will fit into certain other molecules, kind of like a lock and a key. And when that happens, then the molecules will turn into a different shape and do something else. Also, sometimes the shape of the molecule. That's one of the ways that you can taste things or smell things. It depends on the shape. So that's good to know. It talks about biological activity. And that's pretty much it. It gives you a brief, very brief idea of Vesper. But then we're just going to head straight over to 5.2. Because 5.1 is mostly just a summary section. So it's good to know. And if you find yourself looking at the homework and you're like, I can't find this anywhere else, it might be some, vague something from section 5.1. But for the most part, I didn't see a whole lot that was like, you absolutely have to know this stuff in 5.1. All right. So looking at the top of page, what page is this? I have no idea. There's no page number on this one. Okay. Looking just at the very beginning of 5.2, on the first page where 5.2 starts. It starts telling you about valence shell electron pair repulsion. And the whole idea behind valence shell electron pair repulsion is electron pair repulsion. Oh, Spencer, you had a question.
You answered it earlier, but I guess the only thing I would say now is that you're a little quiet for some reason. It might just be me. I don't know why.
Okay. It's probably because I moved it further from me. Is this better?
Yes, it is.
Okay. All right. And sorry for the 5-year-old handwriting today. I have lost my Apple Pencil, which is not good news. And so I'm writing with this giant stylus. So it just is not quite the same. My handwriting is bad to begin with, and when you throw this in, it's even worse. So electron pairs repel each other. And then part of the time this thing doesn't even want to write. Okay. There we go. All right, so it's willing to write here, but not there. Okay. There we go. All right. So electron pairs are going to repel each other, and that's the whole idea behind Vesper. And when I say that, it's basically so when you look at a structure like this that's tetrahedral, it's got electrons in each one of those bonds. And what's going to happen is those electrons are going to repel each other so that they're as far apart as they possibly can be before they start to be repelled by something else. So, for example, this one is going to be sort of in between this one and this one. So my drawing here doesn't show that very well, but it's repelled by this, and it's repelled by that, so it kind of stays in the middle. I guess you can kind of think of it like, let's say you have a magnet here, and a magnet here, and something in the middle, and it's repelled by both of those things, right? Then you could kind of have it kind of hovering in space in between the two, so that it wasn't too close to this magnet and not too close to this magnet, but just kind of in the middle. So the whole reason that the molecules take on the shapes they do is all based on electrons. And when you look at a structure, trying to think of something with a lone pair in it. I'm going to make one up. We'll just, seriously, I hate this thing. Okay. We'll look at CH3 with a lone pair on top instead of it having those, the other H. So if I put a lone pair here, the lone pair is actually going to take up more space than the electrons in the bonds. And it doesn't actually take up more space, but it repels things more. And the reason is because the electrons here have to be shared between carbon and hydrogen. So they're kind of attracted to carbon and they're kind of attracted to hydrogen. But these electrons here are not attached to anything except for carbon. So they're able to repel these electrons more. And so what that does is it forces them closer together. So remember before I said that tetrahedral had an angle of 109.5. So if you have something like the shape that I have drawn here with a lone pair at the top, then that's actually going to give you angles that are less than 109.5 because they're kind of pressed down. Does that make sense?
Yes, it does.
Okay. All right. I wasn't sure. It was silent, and I was like, this must not make any sense at all. All right. It's easier when I'm actually in front of the class, and you can, because I do a lot of hand gestures as I talk.
Out of curiosity, do you know how much, how lesser the angles are, or would that just be something for a computer to estimate?
Well, both. It depends on the molecule itself. Water is something like 104.7. Somewhere around in there is around 104 degrees. So it's not a huge difference. It's slightly different.
Do you know that just because you just remembered it, or?
Oh yeah, just remembered that. So there's no way to really tell without actually measuring the angles. So a lot of times the options that you might have would be like 109.5, less than 109.5, and more than 109.5. Or they might give you some other crazy things like, 180 or something like that. All right, and so we have electron pair geometry and molecular geometry. And that has to do with whether or not you're going to count the lone pairs. When you count the lone pairs, then that's electron pair geometry. So let's say we had something like this. These are all Y's down here by the end. Okay, and then a lone pair here. So if I'm looking at electron pair geometry, then I'm going to count what a lot of people call electron domains. An electron domain is just an area with electrons. They call it steric number here, which is also what it's called. And the steric number has to do with the same thing. So steric number is you count, okay, that's one electron pair, and then 1, 2, 3 atoms connected to it. So the steric number would be 4 here. So that's going to be the atoms bonded plus the lone pairs. All right. So if I was to do this and look at it, and I'm looking at electron pair geometry, then I'm going to talk about where this electron pair is in space. So I would say that was tetrahedral. And because it has a lone pair, that would mean the angle is less than 109.5. All right. So next we're going to look at the molecular geometry, which is based on the electron pair geometry, but a lot of times, not always, but a lot of times it's going to be different. So let's look at that same thing again. Right? And now we're not looking at the steric number. We're just looking at how many atoms are bonded to it. But we're going to kind of separate this out into two things. So it's atoms and then lone pairs. We're going to look at them as two separate things. So I see that there are 3 atoms bonded to it and 1 lone pair. And anything that has 3 atoms bonded to it and 1 lone pair is going to be called trigonal pyramidal. Because they're only talking about, when you're talking about molecular geometry, they want to say, let's say if I have a molecular modeling kit and I put the atoms together, what is it going to look like? And I'm only interested in the atoms, not in the electrons. I mean, not in the lone pairs. So in this case, trigonal pyramidal has to do with molecular geometry, not electron geometry. All right. And then, so we'll go over the kind of the basic structures, and then we're going to go into like, how do you get the other structures from them? So scroll down to the bottom, well, not to the bottom. If you're using the ebook, scroll down closer to the bottom to when you get to table 5.1. And if you're using an actual textbook, flip to, almost said squip, that's not a word, flip to page 206. All right, so we're going to look at this table here. I'm going to show you how to use this and what all you're going to have to memorize. So with this, you want to get started early, as early as possible. So I'd start like today, memorizing this table. And this table is huge, so your first thought is, oh my gosh, she must be joking. But there are ways to make it sort of, there are patterns in the table that make it easier to memorize. So I will show you those patterns. All right. Any questions on anything we've gone over so far? Squip, yeah. Quizlet is good. Let's see. I'm looking through the chat. Okay, so how would you find the angle? Aaron wants to know how to find the angle, and I'll show you that in 1 second. Yeah, no, Chris, the pencil was terribly expensive. And it belongs to work, not me, so that's another problem there. I think the cat found it, and she loves to play with things that are like pencils or sticks as she bats them around the floor, so honestly, it could be anywhere. It's not going to be any fun at all. All right, so, come on. I think my page is frozen. Give me 1 second, because I think my page is frozen. Okay, now it's unfrozen. Stupid. Okay. All right. When I say stupid, I'm talking about my iPad, because it's like, I'm frozen. No, I'm not. So, it's a way to start a Monday back from spring break, right? Okay, so let's look at the first section in table 5.1. If you look at the left, it says at the top in the brown bar, it says Sn equals 3. What that means is the steric number is 3. So if you count all the bonds and all the lone pairs and you add them together, then you get the number 3. So there are two shapes you can get from that. So looking at where you have 3 atoms, then your electron pair geometry is trigonal planar, and your molecular geometry is trigonal planar. So if you notice, what the main thing to notice there is, well, there are two things. One is that the electron pair geometry is the same as the molecular geometry. And see how it has no lone pairs? Every time you have no lone pairs, the electron pair geometry and molecular geometry are the same. The only thing that's going to change the molecular geometry is the number of lone pairs that you have on something. So first they start with something kind of like this. And to figure out the angle, some of them you can kind of figure out thinking through it, even if you forget. And the other ones you want to memorize the angle. So you want to memorize the electron pair geometry, the molecular geometry, and the angle. So looking at this, they're kind of in a circle, right? If I divide, so how many degrees are in a circle? 360, correct. So I have 3 sections of the circle. So if I divide 360 by 3, how many is that? Look, how many degrees? That's 120. And that's the exact angle that we get for this. Here is 120. This stylus is horrible. Like, I'm rubbing it all over the screen. It's doing absolutely nothing. I think it's frozen again. This is not my morning. Okay, now it's unfrozen. Okay. Now it's frozen again. Okay, there we go. All right, so that angle there is 120 degrees. So in between the 2 atoms, it's 120 degrees. None of our mornings. All right, so that's when you have 3 atoms and no lone pairs. All right, 0 lone pairs. Then you get this shape, and it's flat. So imagine if you put something flat on your desk and it's spread out. So all of these 3 things, the X and all 3 Y's, are in the same plane. It's just flat. In the table, they've got an example, and the example that they're showing you is trigonal planar, and you can kind of see that all 4 of those atoms are in the same plane. So that's why they call it planar. And there are three sections, so they call it trigonal, because if you were to draw kind of a straight line, you get a triangle. So that would be that's where they get the trigonal part from. All right, so that's trigonal planar. All right, so let's take a look at when you substitute a lone pair for one of the Y's. All right, so in that case, it's basically the same thing, only at the top, instead of a third Y, we have a lone pair. And actually, I drew that crazy. Okay, that's better. So we still have 3 things, 3 sets of electron areas. The reason I'm saying electron areas is because, let's say we had a double bond there. I'm just going to consider this as one area. So when they talk about steric number and they say how many atoms are bonded to it, how many lone pairs, they do that because it's easier than saying how many bonds, and you're like, well, technically you could say it was 2, but it's double bond, so do you call that 1 bond, or do you call it 2 single bonds, or what? So instead they ask you just to count how many atoms are bonded instead of how many areas of electrons are there. But if you're looking online for a tutorial or something like that, you may see that it asks you how many electron domains are there. And electron domains is going to give you the same thing as steric number. So electron domain and steric number, they mean the same thing. So looking at this, it's going to give you, if you're looking at electron geometry, then I'm going to look at what shape there's going to be when I include the lone pair and the 2 Y's. So that's 3 things connected to the X. And before I had 3 things connected to the X. So what shape would the electron geometry be there? So what was it on the last molecule? So the molecular geometry is going to be bent. That's correct. The electron pair geometry is going to be trigonal planar, just like before. So I'm going to call that the electron pair is trigonal planar. And then the molecular is only looking at that stuff. So it's looking at the X and the 2 Y's. So it talks about molecular geometry. It wants to know what shape are the atoms in. So if you look at the shape of the atoms, they give you basically a bent structure. So if you took a coat hanger and you bend it like this, kind of in that, I'm assuming you have a wire coat hanger, then that would give you the same kind of structure. So they just call it bent. So let's kind of look through the chart for some patterns, and we'll keep going over it. And I'll go over the structures some more tomorrow also, if we run out of time. But I want to show you some patterns in the table that are going to help you memorize some of this stuff. All right, so looking at the table, does everybody know what table I'm talking about? Okay, good. All right. Josh, that's a good question. Why do they call it bent instead of linear? The reason they call it bent instead of linear, so something that's known to be linear is carbon dioxide. So that's linear. And the oxygens are as far apart from each other as they possibly can get before they start getting close to the other oxygen again. So they're linear. And with something that was trigonal planar when it had its electron geometry, but we're looking at just molecular geometry here, they call that bent. And the reason is because even though we're not asking about the lone pair, we still have to consider what the lone pair does. And what the lone pair is doing is it's forcing down these 2 Y's closer to each other, and it's causing the whole structure to be bent instead of linear. So when I say they're not interested in the lone pair, we're just knowing the lone pair is there, but we only want to talk about the shape of the atoms. And the shape of the atoms is determined by how many lone pairs there are and how many atoms there are. All right. So looking at the table, the first part of the table, the steric number is 3. The electron pair geometry for anything that has a steric number of 3 is trigonal planar. And just as a reminder, for steric number, what I mean is it's the number of bonded atoms plus any lone pairs. So that'll give you the steric number. All right, so anything with a steric number of 3, the electron pair geometry is trigonal planar. So you see both of those have trigonal planar. And then if you go all the way past the molecular geometry column, you'll see one that says theoretical bond angles. And below that, you'll see that they both have to do with 120 degrees. The one that has no lone pairs is exactly 120 degrees. And the one that has lone pairs is going to be less than 120 degrees. You can kind of think of, the reason is because it repels the electrons in the bonds of the X and the Y. But you can kind of think of it as, taking up a little bit more space. One way that you can get a good idea of the shape of these in space, and you may have already done this in lab, that's definitely possible, is to take balloons and hold them together at the place where you tied a knot. So basically, in this case, you would have a balloon here, right? And then you would have another balloon here, and then another balloon here. So if it's a lone pair, just imagine there's a bigger balloon there, and it's going to cause these balloons to kind of be forced a little bit closer together because this one's a little bit bigger. So that kind of gives you the same idea of the shape, given that the lone pair has more force to repel the electrons in bonds. So it causes them to be a little closer together. So anytime you see that there are lone pairs there, the angle is going to be less. So if you go down to the next section, the steric number is 4. There are 3 of those, and they're tetrahedral for the electron pair geometry. Looking over at the angle, what's the angle for all of those? Well, 2 of them are less than, but what's the angle we're kind of looking at there? (109.5). Notice that the one that's 109.5 exactly has no lone pairs. The one that has a lone pair is less than 109.5, and the one that has 2 lone pairs is also less than 109.5. But if we were to put them in order from smallest angle to largest angle, the largest angle would be the 109.5. And then the smallest angle would be the one with 2 lone pairs, because it's pushing them closer together. So that's going to be less than 109.5. And the other one is also less than 109.5, but it's kind of in the middle. All right, so when the steric number is 3, there are 2 of them that are trigonal planar. When the steric number is 4, there are 3 that are tetrahedral. When the steric number is 5, there are 4 trigonal bipyramidals. So when the steric number is 3, there are 2 geometries. When the steric number is 5, there are 4. When the steric number is 4, there are 3. What's the pattern that you're seeing here? It's 1 less, correct. So when the steric number is 6, there are 5 of them. Right? So that's one way when you're trying to remember on the test, if you have remembered them all, is, well, if the steric number is 5, you should have 4 different shapes that you're remembering. And then when it comes to angles, you have the angles of 120 for trigonal planar things, 109.5 for tetrahedral things. When it gets to the trigonal bipyramidal, I'll show you why they show you so many different angles to look at. We'll kind of skip that one for now. And then when you're looking at octahedral, 90 degrees. So let's take a look at the trigonal bipyramidal, because we haven't looked at that yet. All right, so trigonal bipyramidal has a steric number of 5. So we're going to look at the first one where there are no lone pairs. So you have some atom in the middle. We'll call that atom X, maybe. Frozen again. Oh, this is driving me crazy. Okay, give me 1 second. I'll be right back. Okay, now it's unfrozen again. Alrighty. Fun, fun, fun. All right, so we're looking at trigonal bipyramidal. Oh, you gotta be kidding me. It's frozen again. Come on. The whole doggone thing is frozen now.
Welcome back from the break, Professor.
Hey, yeah, well, exactly. Oh my gosh. Okay, now it's writing. This makes me crazy. I could kill the cat. All right, so trigonal bipyramidal. So when you have something that's trigonal bipyramidal, you have something in the middle, just like before, and around it, kind of in a circle, making a trigonal planar shape, are 3 atoms. And then above it and below it are 2 more atoms. They could all be the same atom or they could be different atoms. It doesn't matter. So anytime you have the steric number of 5, you have 3 around the middle, all in the same plane. And then you have kind of a straight line that goes up and down. So what do you think the angle between the Y's is? So like this angle, what do you think that is? Yeah, 120. What do you think the angle between this and this is? 180, good. And then between the Z and the Y is 90 degrees. So we've got all right. And so we've got some atom here. And these 3 are in the same plane, just like before when we had something that was trigonal planar. And then this and this are directly above it and below it. So I'm going to be putting something on D2L I think we got 2 minutes left, in the place where I usually put the online tutorials for the exam material stuff, where you're going to find homework and you're going to find the study resources. In the study resources, I'm going to try and find, I'll find a website where you can look at these and rotate them in space so you can get a better idea of what they look like. Because me trying to draw them in 3D, it's not going to give you a good spatial idea of what they are. But when you look at them in the program and you're able to rotate them in different directions, you'll be able to kind of get an idea of the shapes of them. Normally when I teach this, I have my molecular modeling kit with me, and then I just build them for the class and I show them to you. But my molecular modeling kit is maybe still in my office that I haven't seen in a year or something now. And then there was a flood, so I hope it still exists. So who knows? But anyway, so that's why I'm going to put the program on there, or the website, so that you get an idea of kind of what they look like. And we'll go over more on Wednesday, kind of the different shapes that there are. But in the meantime, be memorizing this chart. So what you're going to memorize is you're going to memorize the molecular geometry, the electron geometry, and the angle. And in order to figure those out, you have to know how many atoms are bonded to it and how many lone pairs. And I'll go into more detail on Wednesday when hopefully I can write on the board, assuming I find this stupid thing. Okay, anyway, so you guys hopefully will have a better day than I'm having so far. And I will see you guys on Wednesday. Don't forget there's going to be a quiz on Wednesday over the reading. Not today's reading, but the reading that you have to do for Wednesday. All right? And I will talk to you guys later. Bye. See you Wednesday.